Well, it is a great pleasure to be here today following the award of the Japan Prize yesterday, which was certainly a great honor to me. And what I'm going to try and do in this talk is reflect on some of the research that I've done over many years, 40 to 45 years, which formed the basis of the citation which was given on the award of the prize. And I will cover two bodies of work. But before I do that, I'd like to reflect on the situation that I've found in the late 1960s, early 1970s, when I started my research. So by that time, there was a huge body of practical knowledge of how the atmosphere behaved, how weather systems behaved. Many years of people looking at the weather in their particular location of the world. But compared with that, the theory was really very basic. There was a body of theory, but it was usually based on very approximated equations, on small amplitude, very weak systems, and on simple geometry. So there was a large gap between the weather systems that were observed and the theory at that time. However, amazing opportunity, because we were starting to get the observations from instruments on satellites, global observations every day. So this was a whole new world that was presented to us in terms of the behavior of the atmosphere. But in terms of the modeling, there were now computers that were becoming powerful enough, and the models had been, numerical models had been developed enough that they could, on these more powerful computers, produce reasonably realistic behavior of weather systems and of climate. So there was an opportunity to use those same models on those computers as a sort of laboratory tool to help bridge the gap between the theory and the observations. And that's what I tried to do. And that was the real opportunity at the start of my career. So the first area I want to talk about is the growth of cyclones, of low pressure systems, and of the fronts on them, and our understanding of low pressure systems that then can give extreme weather. So 100 years ago, the Norwegian frontal model or Norwegian cyclone model had been developed based on observation and producing a conceptual view of how the atmosphere behaved. So the view here is of the initial front, a front around a discontinuity surface between the warm air to the north and to the south and the cold air to the north, a discontinuity surface through the atmosphere. And that frontal surface buckles, it has a wave on it, and that is how they envisaged a cyclone, a low pressure system developing. And this low pressure system has a cold front to the back of it and a warm front in there. And those are the rapid transitions between the cold and warm air. The cold front moves more rapidly than the warm front, catches it up, and the cyclone reaches its maturity and then decays, and one is left again with the front. So the front leads to the cyclone on it and back to this discontinuity surface. 100 years later, a typical weather map still has this Norwegian conceptual model. The picture here is actually for one of the extreme cyclones that we've had in recent years, just approaching the UK. However, I'm sure many weather maps you've looked at looked the same as this. So the Norwegian view is at the top. However, the theory that was developed in the 1940s and 1950s started from an alternative perspective of the contrast in temperature between the polar regions and the tropical regions, but as a more distributed contrast. And associated with that contrast would be westerly winds that increased with height. And weather systems were seen as an instability of this broad temperature contrast. And then fronts were envisaged as being developed in those weather systems. And finally, the mature weather system then with its fronts leads to a changed large-scale state. And that's the picture that was starting to emerge and one that my work helped to contribute to. So the observations, for example, the one on the left here shows a strong surface front, not a discontinuity surface throughout the atmosphere, but strong just near the surface of the Earth. And the contours here, the continuous contours, are those of a temperature that takes account of the compressibility of the atmosphere, and it's called potential temperature. And the dashed contours are those of the wind. And in this frontal region are both strong temperature contrast and strong wind contrast, but only near the surface of the Earth. The picture on the right shows the other fronts that were being observed. And this one is in the upper troposphere. The troposphere is this region down here, the lowest 10, 12 kilometers of the atmosphere, where most of the weather occurs. But above that is the stratosphere. And this time you can see that the strong contrasts are in the upper troposphere in both wind and temperature. And associated with this, there is a strong jet here, the strong wind speed maximum. So here the gradients are only in the upper troposphere, and in a number of ways, they found that this air originated in the stratosphere. Here on this, which you will not be able to read, there are measurements of radioactivity that identified the air as having originated in the stratosphere. So we have no longer a discontinuity, but surface or upper tropospheric fronts forming in these weather systems. And this is Francis Bretherton, who first taught me a course in mathematics, but a mathematics applied to understanding how the atmosphere moves. And that was really stimulating for me. And I asked him if I could do a PhD with him, and the topic was the formation of fronts in the atmosphere as a mathematical problem. So the sort of situation we looked at is where there is cold air here on the left, warm air on the right, and this is the vertical direction, and the large-scale atmosphere is moving those two together to increase the temperature gradients. And the atmosphere responds, as was already known, in terms of the warm air rising and the cold air descending. And this circulation, if we look at low levels, it then moves the temperature field, the colder air towards the warmer air, producing convergence. So it makes the temperature contrast stronger. But this is only on the warm side of the temperature contrast. And at the lid here, there is also a front on the cold side. But what we discovered was, as the contrast in that frontal region becomes stronger, contrast in temperature and wind, so the convergence in that produced by that circulation becomes stronger. And that leads to the formation of a discontinuity in a finite time in this mathematical model. So we see how strong surface fronts form. And if we look close to that frontal region, in this top picture here on the right, you can see the temperature contours close together and the warm air rising over the frontal, what looks like a frontal surface, but it is purely the dynamics of the atmosphere that is producing that. In the bottom right, we see the result of no longer having a lid on the atmosphere, but putting a stratosphere on top. So in this case, that frontal circulation drags down part of that stratospheric air in a tongue of stratospheric air almost along the potential temperature contours. And you can see also that there is a jet there. So we can produce quite a realistic upper air front as well as a surface front from these ideas. So the next move was to actually try and look at these sort of occurring in a model weather system. So we were able to extend this model to produce three-dimensional distribution and the growth of a weather system. So here we have a low-pressure system and a high-pressure system. Already the low-pressure system is more concentrated than the high-pressure system and stronger. But of interest, particular interest to us, was the gradients along this cold front region are much enhanced. So we can produce a cold front in this model. We don't have a strong warm front, but we do have a front along the northern air region of the cyclone. So the question for us was, could we produce a strong warm front? And we found that if we change the basic state to have some westerlies on the southern flank and on the northern flank, then the weather system bent with those ambient shears and produced, instead of a cold front, a strong warm front. So we can get those behaviors, but only from rather different situations. So we then moved on, and this was work with my colleague Adrian Simmons, where we took a more complex, less approximated model, and we ran that on a computer. However, we didn't run it as a weather forecast. We said, what happens if we have cold air in the North Polar region, warm air in the subtropical region, with a contrast in between? And we determined what weather patterns would grow fastest. And we imposed a particular symmetry around the hemisphere where there are 6 waves around the hemisphere, and I'm showing 2 here. So this is after running the model for 3 days where the magnitude of the wave has increased. And you can see then we do have a low pressure system developed, a high pressure system, and the warm air is moving towards the pole here, and the cold air is moving towards the equator here. So I'm now going to show you how this develops very rapidly over the next 2 days from day 3 to 5. We will see the rapid growth of the low pressure system in particular and of the sort of fronts on this situation. So I will run this a number of times, and that's growing up now up to day 5, and it becomes starting again. So you see the growth of these weather systems, the warm air and cold air moving, the warm air moving towards the pole, the cold air towards the equator. And if I stop that at day 5, this is the quite realistic weather pattern that we've achieved in this very simple situation. So here you see the low pressure system much more intense than the high pressure system. And you can see the warm air moved polewards and round in the low pressure system. The cold air moved equatorwards, and there are strong gradients in this region, as we'll see in a moment. So that is the weather system growing just from that smooth state that we started off. And if we now look for the next 2 days, so we will look for the growth from day 5 to 7, during this time, the wave will reach maturity and we will start to see the decay process. So we now see the weather system growing and starting to be very mature, and in fact, the wave in it starting to decay. So if we look at day 7, then we see a situation in which the warm air is trapped in the low pressure system, but otherwise there is only warm air in the tropics. The cold air has moved and is a broad region in here. So we have lost the mid-latitude temperature contrast. Warm air has been transported towards the polar region, warming that up. Cold air has been transported towards the equator and cooling that off. So you see weather systems actually smoothing out the temperature gradient, removing the temperature contrast. Now, if we return to that day 5 to concentrate on surface fronts, here we're showing surface temperature in the colors as before, but also the contours show surface temperature as well. And this is the front. We were seeing the cold front here on the warm side of the temperature contrast, and again north of the low pressure system. So the question that Adrian and I talked about then was, can we produce a strong warm front? And indeed, we followed the advice of the previous model and said, let's try putting some strong westerlies near the surface in the warm air south of the weather system. And again, the whole weather system responded in its tilts, and it produced a strong warm front. So we started to gain an idea of the sensitivity of weather systems to the ambient flow. I should say that these very nice simulations were not the ones that Adrian Simmons and I produced some 40-odd years ago. They are ones produced much more recently by John Methven, and these very nice, at much higher resolution than we could have used, and also these very nice video pictures. But now I want to move on to showing the situation in the away from the surface and up around 10 kilometers in the atmosphere, so that we can see what happens in different regions. And the map I'm going to look at is one of stream function. And stream function shows the direction of the flow. Here we see the westerly winds blowing around here. And where the contours become close together, that means the wind is strong. So at day 3, you can mainly see the westerly wind, but with a slight wave on it. And what we're going to look at next is how that wave, how that system behaves from day 3 growing on to day 9. And what we will see is the wave growing on the westerlies. It then tends to curve and break like the waves on the ocean. And in breaking, it decays and we achieve a different state. So that's what I'll show you now. And this is the development over the next 6 days. And you can see the weather system grow. It's starting to have large tilts on it, and those waves break, and you're left with very little wave, but a stronger westerly wind, and in a different region. So the wave grows and breaks, and we're left with those westerlies in the northern region. So if we capture that day 9 flow, this is the situation we reached. But again, the sensitivity, we see that this situation, this wave, this weather pattern, as it has grown, we've already talked about it removing the temperature contrast, and we can see that it has actually also moved the westerly winds poleward. So the weather systems themselves change the basic state. But now the question is, how does that other weather system, the one with the strong warm front, behave? And at day 9, this is what it looks like. So this is the extra westerlies here. And instead of this wave-breaking decay behavior, we get very large cyclones forming. And these cyclonic eddies will then persist for weeks. So that is a very different development. And it's very important, the sensitivity of weather systems and their growth and decay to the ambient flow on which they develop. As a last aspect in this part of my talk, I want to give you a glimpse of another perspective we have used to discuss atmospheric weather behavior. And that is based on something called potential vorticity, which is not easy to keep saying, so we call it PV, which is much more understandable. And the general development was in a work with Michael McIntyre and Andy Robertson, my student. However, the particular aspect I'm going to show you here about the growth of the weather system is one developed with John Methven and Isle Heifetz, and also Chris Thorncroft has been involved in this as well. So I'm going to concentrate on the day 5 situation, and the colors show you the behavior we've looked at already with the warm air going polewards and the cold air equatorwards. But the other contours are ones that tell you about the flow in the upper atmosphere, the upper troposphere. And these are contours of potential temperature, which we've already mentioned, but on a particular PV surface that behaves very similarly to the tropopause. So if you like, we're looking at a form of temperature on the tropopause. And the argument goes here that the warm air near the surface produces its own cyclonic flow, its own as a low pressure system, if you like. And that cyclonic winds, the winds we have there, the north-south winds, then extend through the atmosphere and influence the upper troposphere. So if you look at the phase of this, then this motion poleward here acts to amplify the upper wave, and the motion equatorward here acts to amplify this part of the wave. So the upper wave is actually, the behavior in the upper troposphere is amplified by the circulation from the lower troposphere. But equally, if we look at what is produced by the cold region here, for example, then the white arrows show you the circulation produced by that. And this extends from high levels down to near the surface and acts to amplify the low-level wave, moving that poleward and that equatorward. So each wave acts to amplify the other. And we can also show that each wave tends to lock the two together. So the two waves amplify each other and lock on so their growth can continue. Now, I could go on for a long time on this, and there have been many developments of this which help one understand extreme cyclones and also show comparison with the observations that Mike Wallace and his group took years ago as well. So we see the basis of understanding extreme cyclones. But I now want to move on to the second part of my talk, which is on teleconnections, or the far-field influence of something happening in one region of the atmosphere. And there was a background to this by Ye Duzheng, as he's known in more recent years, back in 1949. And the situation he considered was one in which there is a westerly wind, and at day 0, in a very simple model, you put on a forcing which makes the air want to go poleward. And you see that the air does go poleward and produces what we could think of as a high-pressure system here. However, that high-pressure system has its own circulation like this, and it tends to move this air equatorward. And so we start to develop a wave downstream. This low-pressure system develops its own circulation and moves the air equatorward, poleward again. So we see a wave developing downstream. And those waves are known after Ye's supervisor, Rossby. So these are Rossby waves. And you can see that within 3 days, the atmosphere a long distance to the east knows that there is a forcing going on here and has its influence. So this simple theory then provided the basis for looking further at this. This theory is for a uniform westerly wind. It's on a plane, and it only considered this eastward propagation. So I considered then the propagation not just in that eastward direction, but also in eastward but northward or southward. And the wave information moves at twice the speed of the westerly flow in this direction. It moves slower in those north or south directions, but it can still progress to the east. And you can show that within a certain time, the waves of the same wavelength will fill the circle downstream from the forcing region. So those waves go in straight lines. What happens when we move to the sphere? And the obvious thing is actually what happens, that instead of the propagation being on straight lines, it is on great circle paths. And this shows the simplest Rossby wave on the sphere for an atmosphere that is moving round slightly faster than the planet. And the Rossby wave like this says, for example, that something that happens over here in the equatorial region can impact Japan a few days later. And if it goes on occurring, this can produce an anomaly that might last a month or a season. So that is a very simple model. And then with Dave Caroli, whose picture is shown here, who was a student of mine, we looked at a more complex model, and with a more complex flow of westerlies and easterlies, as in the atmosphere. And we also looked at what is the response to heating in this region here. That heating could be due to convection over anomalously warm water, and it produces what we would expect by now, a succession of waves going along almost great circle paths. But you can see that departs just a little from that. You can get some waves doing this and longer waves doing this and even close to the pole. But we see the same as we saw in the simple model before, that something happening in one region of the globe can influence almost anywhere to the east of that. And in particular, the tropics can affect the extratropics. And this provided a theoretical basis, but at the same time, Mike Wallace and his group were providing an observational basis, and we were both very happy to see what the other had produced. And this gives a basis, again, for the sort of anomalies that you might have in a particular season, or maybe in climate, where you can understand the impact globally of what happens in a certain region. So moving on to another simple model, but this is actually a simpler model, but it does allow both the use of the observed westerlies and easterly winds, and also particularly looking at large amplitude heating. And this was done with Prashant Sardeshmukh, where we looked at the impact of a near equatorial heating region in the presence of the westerlies and easterlies and with large amplitude. And the lower picture shows what you should expect by now with waves going out into both hemispheres, plus minus, along almost great circle paths. We put some damping in this model, and that allows the steady situation to be achieved. And if you take those waves and the basic westerly and easterly flow, then you get the total stream function as in this here. Where they're close together, you have the subtropical jet, and where they're far apart, the flow is weaker. This is the observed situation in the Northern Hemisphere winter. And we see many similarities, that there are strong jet here off Japan. There is the situation of the flow into North America. There are westerlies on the equator, and there are easterly winds on the equator. And over this part of the sphere, hemisphere, of the whole sphere, then the situation is remarkably close to the observed. But we can see with the absence of the Rocky Mountains, we don't get this wave pattern here. However, what we've taken is a very simple model, just put in the heating that occurs over the warm waters in the West Pacific, tropical Pacific, and we get a very good first answer for what the flow looks like. And of course, if that heating is different from normal, or the sea surface temperatures are different from normal, so this pattern will be different from normal. So that may be in a seasonal context, or it may be in a climate change context. So we've already seen that Rossby waves can be refracted and reflected almost like rays of light, and you can use the same theory as Tercio Ambrizzi and I did. And in particular, you can show that a strong westerly jet can trap these waves and act as a wave guide. And I want to finish this talk by showing you a few situations in which that is very important as well. So these are two pictures for summer situations, Northern Hemisphere summer, and I've shown one which was actually associated with floods in Pakistan and the other with floods in India. But if we look at the upper picture, then in the Northern Hemisphere summer, there is a strong wave guide all the way from the Mediterranean through to Japan. It runs north of the westerlies, go north of the Tibetan plateau, and that then can act as a wave guide and often does. Now, in this situation, the waves are very high amplitude. There had been a lot of forcing from upstream here, and the stationary waves are there present. And if we look at this strong trough here, that is just west and north of Pakistan, where the floods occurred. And every time there was an enhancement of this wave pattern in the region of the UK, then a few days later, there was a flooding event in Pakistan with these regular waves going down the jet stream, down this wave guide. So very orderly behavior, quite predictable on the timescale of a few days. And also, if you know about the structure of this jet in one year compared with another, or in climate, you can think about the different behavior. And the second picture then shows a floods in India, where we again, it is different upstream this time, but again, the strong wave guide. And in this case, that trough is slightly further east, and it is India that got the floods this time. Then you can see Takeshi Enomoto here, a Japanese postdoc with me, and he looked at this wave guide across the north of the Tibetan plateau and used the very good name, the Silk Road, for that wave guide. And he used models and observations to look at situations where there was a forcing of waves, in particular by descent on the western side of the plateau. And these waves then move along the wave guide, and they accumulate near Japan. And he found that the impact of those waves was to tend to force the Bonin high in summer. And that leads to a very warm, a hot, dry Japan in late July and August. So again, these simple ideas lead to concepts, ways of understanding extreme behavior. So I hope I have given you some interesting examples of the sort of work we've done, which can enable to understand extreme weather or changes from one year to another or changes in climate. And with the work of Mike Wallace, these were seen by the JapanPrize Foundation as being the foundation, providing a foundation for enabling prediction of extreme weather and its change in climate. So it is understanding how the atmosphere behaves is really challenging. You can't do an experiment with it, but you can try doing experiments with models, and you can use theory. It's absolutely fascinating, and it's been very rewarding as a human being to see that this is actually of use, that the predictions can then follow from these. And I continue to be fascinated by it. Thank you very much.